Hello, we're glad you've joined us for this live webinar, Understand the Rationale Behind the Q-TOF LCMS that Stably Sustains Sub-ppm Mass Accuracy. I am Judy O'Rourke of LabRoots, and I'll be moderating this session. Today's educational web seminar is presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. It's brought to you by Shimadzu Corporation. Shimadzu Corporation provides cutting-edge analysis technologies that are contributing to research, technology development, and quality control in a wide variety of fields. The company carries out research and development into improving the performance of mass spectrometry technology that is currently finding increasing application in life science areas such as drug discovery and medical research. To learn more, visit www.shimadzu.com. I now present today's speaker, Atsuhiko, known as Ash, Toyama, PhD, Mass Spectrometry Application Specialist in the Analytical and Measuring Instruments Division at Shimadzu Corporation, based in Japan. Dr. Toyama has 10 years of proteomics research experience. His areas of expertise also include quantitative mass spectrometry with a particular focus on bioanalysis, metabolomics, and endocrinology. At Shimadzu, he has been involved in academic research collaborations, application development, and specification development of mass spectrometers. Dr. Toyama has a Master of Science degree in biochemistry from the University of Cambridge in the UK and a PhD in biological sciences from the University of Tokyo for his research on clinical proteomics. Dr. Toyama will now begin his presentation.
Thanks, Judy, for the introduction. So my name is Ash Toyama, and I am the Mass Spectrometry Application Specialist of Shimadzu Corporation. And the title of today's presentation is to understand the rationale behind Q-TOF LCMS that stably sustains sub-ppm mass accuracy. So LCMS-9030 is the Shimadzu's first Q-TOF, and it's been launched this year, this June 2018. And the photo shows here shows one of the first installations in Australia, and on the left is my colleague, and on the right is my collaborator. So let me take a few slides explaining how we came to this Q-TOF. The engineering concept of this Q-TOF instrumentation is effortless performance. So conventionally, Q-TOF has been a very, very naive instrument to utilize in routine. So you have to tune and calibrate every so often to get the proper data. And even if you've got the data, you've got to calibrate again to ensure that you've got usable data. So our intention was to change this user experience to something more organized and more productive, such that you tune once and you calibrate once and you keep on generating the usable data. And how we came to this is by focusing on the mass appeal. So mass standing for MASS, standing for mass accuracy, sensitivity, and speed. And today I will focus particularly on the mass accuracy and the stability of mass accuracy, which I believe represents the overall performance of a Q-TOF in high-resolution accurate mass instrument. So here are today's topics. I would discuss how various parameters affect the accuracy of mass measurement, and I will demonstrate the mass drift caused by temperature change. So these will demonstrate to you what sort of things you need to be careful about when operating in routine the high resolution accurate mass instrumentation. And we would learn how to assess whether this HRAM-MS is practically capable of measuring at sub-ppm mass accuracy. And here's a quick recap of Shimadzu's LCMS-9030 Q-TOF. So according to the specification, the mass resolution is 30,000 FWHM at M/Z 1972. And mass accuracy is better than 1 ppm at M/Z 622. And mass accuracy stability, which is our unique specification, is that we sustain 1 ppm mass drift over 24 hours at a constant temperature between 18 to 28 degrees C. So I'd like to start by just recapping the notion of accuracy and precision, and this is in general. So shown are 4 pseudo mass spectra showing accuracy and precision. So the top chart in red shows the accurate and precise data, which is what we want. So if our expected mass is 400, we would expect all signal to fall around 400. But you could get still accurate data without precision. So that's the second one in green. So the average measured mass, the mean measured mass, is still exactly at 400. So this is an accurate data, but each individual data point are imprecise. Whereas on the other hand, you could get a chart like a blue one. You could get a very, very precise data, but inaccurate. And of course, you could get neither inaccurate and imprecise data, which is what we do not want. So starting from the definition, IUPAC defines mass resolution as the m over delta m, where m is the mass of the ion of interest and delta m is the peak width. And what's important to note here is that conventionally we define this mass resolution. We use the peak width definition, which is 50% of height is typically used and denoted as full width at half maximum, FWHM in short. So this is depicted in the diagram below. So for example, for a mass of 300, and we observed that the FWHM was, delta M was 0.01, then it dictates that resolution at that point is 30,000. And this is typically what we observe in the Shimadzu instrument. And on the other hand is the definition of mass measurement accuracy. Mass measurement accuracy, MMA in short, is defined as the deviation of measured mass from the exact mass. And here exact mass means the calculated theoretical mass. So MI is denoting the individual mass measurement, and whereas M exact is the theoretical exact mass. And it is customary to specify MMA as a relative unit expressed in parts per million, ppm. So diagram below shows derivation of mass measurement accuracy from a measured mass spectrum. So this is a mass spectrum, and you observe a peak apex or peak centroid, which represents the individual mass measurement, and you measure the delta M, the mass deviation from the theoretical mass, and you show that as the error in ppm. So in order to further deepen your understanding and to grasp what factors affect mass accuracy, we need to understand this mass measurement phenomenon in terms of ion statistics. So this diagram is a very simple schematic aimed at demonstrating how what is actually happening in the mass spectrometer. So we have a population of ions. So these have the exact masses, and we are sampling these ions from this population at a finite mass resolution, which is with errors. So you end up with a distribution of measured masses. And because it's a statistical phenomenon, we can assume normal distribution. And if you assume normal distribution, then it dictates that precision of mass measurement is the standard deviation of mass measurement. So diagrams below show the normal distribution of mass measurement, and plotted on the x-axis is the standard deviation. So in this chart, you can see that FWHM corresponds to about 2.35 of the sigma, and this can be derived or proved mathematically. So mass resolution and precision are interchangeable terms. And because it's normally distributed, we could assume that 95% of data will fall under plus or minus 2 sigma. So let's consider a single sampling event, single sampling of an ion from the population of iron. So for a mass resolution of, think of a mass resolution of 30,000 and exact mass of 400, we could say that FWHM is 0.0133, and expected standard deviation is 14 ppm. So we could deduce that at single measurement, at 95% of the cases, a single measurement will result somewhere around this 400 m/d, plus or minus 2 sigma, plus or minus 28 ppm. And repeatability of this measurement is directly related to resolution, and this dictates the mass measurement accuracy of a single ion. So this sounds as though mass resolution is an extremely important factor for achieving good mass measurement accuracy, but that's not the end of the story, and we have to consider a different factor. So in reality, mass resolution alone does not guarantee good mass measurement accuracy. So let's consider now sampling of multiple ions, which is what happens in reality in mass spectrometers. So from the population of ions, let's say you're sampling thousands of ions. So what we end up is a distribution shown in red, which is the measured experimental distribution. And this has the measured mean mass, which is the apex of this red distribution. And in this particular example, this distribution is slightly different from the expected theoretical distribution shown in blue. So we observe a deviation in the measured mass from M exact. And this is purely due to the limitation in the number of sampled ions. So this is why experimental distribution is always slightly different from the expected distribution. And this distribution itself has variation, and the standard deviation of this mean is a real mass accuracy. So experimentally measured mass is the mean of all individual ion measurement, and by increasing the number of ions being sampled, you would expect this experimental distribution to converge or go very approximate the theoretical distribution. So what I'm trying to say here is that it's not just the resolution, but also sensitivity, or the number of ions being sampled in a single measurement, is an important factor for getting good mass accuracy. And mathematically, this can be represented as shown. Theoretical limit of mass accuracy can be shown by calculating the repeatability of experimentally measured mass, so such that standard deviation of this measurement is standard deviation of the individual ion measurement, which is dictated by resolution, divided by the root of the number of ions being sampled. And this is proportional to 1 over R root n, and n being the number of ions being sampled. And in this table, and in the center, this shows the relationship between ion statistics and theoretical limit of mass measurement accuracy for mass resolution of 30,000. So for an instrument of 30,000 resolution, if you sampled one ion, it's 28 ppm. But if you're measuring 1,000 ions, the theoretical, the best performance we would expect to see is 0.9 ppm, 95% confidence interval. And if you've measured 10,000 ions, it's 0.28 ppm. So even with an instrument of 30,000 resolution, we should ideally achieve better than 1 ppm error in this practical range of detection, because normally you're not just measuring 1 or 10 of ions, but you're playing around with thousands of ions. So I've shown this relationship in a triangle. So what's important in accurate mass measurement are the three factors: resolution, sensitivity, and sitting on top of these are the stability. So I've denoted this relationship as K over R root n. Resolution is important for individual ion measurement, and sensitivity is important because you need to sample sufficient number of ions to get to approximate the distribution to the theoretical distribution. So now the important factor again is the stability. So shown here are several factors that are affecting the stability of mass measurement. And there are two main sources of error, one being systematic error and the other being non-systematic error. And systematic error is also called a bias. So you have a good reason for not being able to measure accurately. And this can be temperature fluctuation, of course, which is an important factor in a Q-TOF instrument, and a dead time effect of a detector, particularly with a time-to-digital converter. I'm not going to describe this in full detail, but what typically happens in time-to-digital converter is that when this could get saturated quite easily. So what you observe is that when you have really high signal intensity, this signal is measured at a slightly lower mass than expected due to detector saturation, and vice versa. So this could introduce another bias. Or you could introduce bias by not selecting the appropriate calibration standard, because calibration is never perfect. So this is something like, say you're measuring an M of Z of 400, and you're using a calibration standard of M over the 200 and 600. So 400 is quite far in M of Z from 200 or 600. So calibration at M of Z 400 isn't as perfect as 200 or 600. So you've got to select the appropriate calibration standard in order to be able to measure accurately. Otherwise, you're introducing the bias at the first place. So these are the systematic errors. Whereas non-systematic errors are randomly occurring phenomena, such as due to lack of electronic robustness, or interference from chemical background, or inadequate mass correction using log mass if you're using it. So this means that if you're using log mass and by any chance you didn't measure the log mass signal correctly, then it it messes up the rest of the mass spectrum. And this slide describes how temperature affects mass accuracy in a Q-TOF instrument. Just to recap, so in a quadruple time of flight instrument, what you're measuring is the time of flight of ions, and this time of flight depends on the length of the flight tube, and this length changes very slightly but measurably by expansion and contraction, physical expansion and contraction of the flight tube. So if the temperature increases, then the ions are traveling for a longer distance and the measured mass is shifted to the higher value. And vice versa, if the temperature goes down, you would expect to see a negative bias to mass measurement. And typically, a few degrees C change can result in tens of ppm of mass shift from the point you calibrated. And this data is extracted from the literature shown, a paper in 2014. And the data show, the chart on top shows the temperature shift, and the chart on the bottom shows the mass accuracy error at the same time. And this mass accuracy error is coming from the log mass ion. So these ions are constantly measured, and because these are the log mass, you can observe the mass error before being corrected. So we could see that as the temperature shifts, the y-axis of this mass accuracy error is tens of ppm. So for a temperature change of plus or minus 0.51 degree, you observed a mass error. Without log mass calibration, it shifted by maximum of 33 ppm. And you could see that once it shoots off, then it never comes back until quite a while. So this is what conventionally we've been observing and we've been experiencing with the Q-TOF mass spectrometers. And this is why we were thinking that log mass calibration is a mandate. So whether we're observing this in our instrument, we've checked in this quality center at Shimadzu headquarters. So in Shimadzu Corporation in Kyoto, we have one building block fully dedicated for product quality assessment. And here we can perform tests under harsh environment, like extreme temperature change or humidity change, or you could subject it to electronic stress, or you could even drop it. So we've brought in our Q-TOF instrument in this metallic room where we can control the temperature very accurately. And we've done a 24-hour batch hourly measurement of the calibration standards, and we've shifted the temperature up by 3 degrees, and then down by 6 degrees, and then up by 3 degrees again, back to the original temperature. And this happened in 24 hours. This is an extreme case. You don't expect to see that much temperature fluctuation in a laboratory environment. But we've done this to see how temperature might affect our data. And this is the result of the temperature stress test, plus or minus 3 degrees in 24 hours. And we're showing here 6 compounds, and the black trace in dotted line, this shows the temperature change, up by 3 degrees, down by 6 degrees, and up by 3 degrees again. And these are the actual measured temperatures in this controlled environment. And the blue dots represent the mass accuracy, mass error in ppm. of the individual mass measurement over the 24 hours. So we could see clearly that the black dotted trace, the blue mass accuracy trace, follows exactly the trend of the temperature. And the extent of mass drift, we've seen that it's within 1.5 ppm, plus or minus 1.5 ppm. And similarly for the negative mode, 0.9 ppm mass drift, 1.1 ppm mass drift. So results showed that all the data in this stressed environment, we observed less than 1.5 ppm mass drift, and all the data points fell under 3 ppm mass error. And this is only by one single external calibration conducted before the experiment, and no log mass was used. And this clearly demonstrates that the real flight temperature is super stable. So everything's under control. So we've seen that the temperature is more or less under control. And our instrument is actually using analog to digital converter to minimize the dead time effect. And so this shows that if we've selected the right calibration standard, we could get rid of most of the sources of systematic error. So we'll be left with non-systematic errors. So how would the data be without these systematic errors? And this is what we've conducted. So we've done another experiment, this time over 60 hours at a controlled, stable temperature environment. And this data shows the mass accuracy stability over the 60 hours. And this is only by a single external calibration conducted before the experiment. So here, the results for 14 compounds are shown, 18 positive mode and 16 negative mode. So over the 60 hours, all the data points fell under 1 ppm mass error. And individual data points shows the mass accuracy at hourly measurement, and you could see that most of the data points are superimposing on top of each other, showing that the data are highly repeatable. And this table is showing the same data in numbers, and I'm not expecting you to read all of these numbers, but I'd like to draw your attention to the second column from the right, shown in yellow. So this column shows the mean error in ppm over the 60-hour period. So we've averaged all the mass accuracy over the 60 measurements, and this average is very much close to zero, 0.002, 0.02, 0.09 ppm. And this is a statistically correct phenomenon because we've shown before that mass measurement accuracy is K over R root N. So if N increases, then it follows that the error decreases. And we've done this for 60 hours. We've done 60 measurements, so we're sampling quite a few number of ions. So we're expecting to see that mean absolute error converges to zero. So this also shows that we're experiencing no mass drift or any systematic error that are causing the bias. So all data under the same external calibration, no bias or drift was observed. So this leaves us with just with the non-systematic error, and this is represented by the standard deviation of individual mass measurement. So without the systematic error, standard deviation of multiple measurements represents the degree of system stability against non-systematic error. So this we've shown over the 60 hours, over 60 measurements. And just note here that frequently what's used is the relative mean square, which is approximately equal to the standard deviation, but often used for a small number of repeats. So, in summary, if we put all the systematic error sources under control, we're left with the non-systematic errors, and we've shown that our instrument is extremely robust and stable, and so this leaves us with no need to use the log mass correction. So having shown this, I'm just going to go back to, well, introducing our instrument, how we put everything under control, and particularly the temperature. So temperature stability, the stability against temperature fluctuation is solely governed by this flight tube temperature control system, and this is where we've spent a lot of time on in our development. So we've implemented 3 features: computational approach to optimization of heater and sensor positions, novel feedback feed-forward algorithm, and thirdly, the patented nickel plating technology for maximizing radiation. And actually, this nickel plating technology is something we're implementing in a testing machine and in a turbomolecular pump. So I'm going to describe very briefly the optimization scheme, because this is what's actually affecting the data. So optimization is the term used in mechanical engineering. We've got to analyze the object to identify the stress points of objects. This is what's conventionally done in mechanical engineering. And we've taken the same approach for heat control, because quite recently, in 2016, it's been shown that heat does not conduct uniformly, but in waves in the first instance. And this phenomenon is very similar to vibrational modes. So because it's similar to vibrational modes, we could use the same algorithm to predict the hot spots and cold spots in our design, and we could change the position of heater and sensors accordingly to optimize and to mitigate this inefficiency in heat conduction. And this is exactly what we've done. So in conclusion, we've balanced the stability and resolution and sensitivity to achieve better than 1 ppm error in a stable fashion. So here are the key takeaways. So achieving good mass accuracy is a balance between resolution, sensitivity, and stability. And we've shown that 30,000 resolution was sufficient, more than sufficient, to deliver better than 1 ppm mass measurement accuracy. And this was achieved by high sensitivity and stability. And temperature fluctuation is the most critical issue for any Q-TOF, often necessitating the use of internal calibration or correction. But we've addressed this quite nicely, and we've alleviated the need for internal correction. And achieving 1 ppm mass measurement accuracy in one measurement can occur by chance. We've got to consider mass accuracy in terms of ion statistics. So benchmark should really be the standard deviation of error through a series of analyses. And we've achieved standard deviation of 0.2 ppm over the 60-hour batch without recalibration, showing remarkable stability against non-systematic errors. Okay, so in the next few slides, I'm going to describe why mass accuracy is important in real applications. So using high mass accuracy data can happen in several ways, and an example shown here is detection of pesticide from matrix by just measuring MS1. So if we have a database of retention time and accurate mass, we can simply extract from MS1 data the signals corresponding to these accurate masses and if those detected XIC corresponds to the retention time, we could deduce that we've detected these pesticides. So this can be a very brief and very comprehensive screening method. But this by itself isn't sufficient for identification. We could further verify this identification by comparing the exact masses and the measured masses, and as well as the isotopic abundance ratio. So if we compared the measured spectrum to the theoretical spectrum corresponding to the empirical formula, we could assign correctly that this detected signal was surely of this empirical formula corresponding to fluorophenoxamine. So the reason why mass accuracy is important is shown. So if we take this approach, what's important is the setting of the mass accuracy window when doing these searches. So we've done two things here. We've extracted data by showing the extracted ion chromatogram. A mass accuracy window is applied here, and we've done the formula prediction, and mass accuracy window applies here as well. So if we've conducted this formula prediction at mass accuracy of 1 Dalton, then it gives 4,000 different combinations. So we've got to narrow down these number of candidates by setting the mass accuracy window as small as possible. And this diagram shows the importance of mass accuracy window in creation of the extracted ion chromatogram. So if we set the mass accuracy window too wide, then you would incorporate noise signal into this XIC, and you would end up with high noise and low SN ratio. Whereas if you set the mass accuracy window too narrow for your the real mass measurement accuracy, then you would sometimes get missing data points because your data accidentally fell outside of this window. So it's really important to set an appropriate mass accuracy window for these analyses. So the conclusion of today's presentation is that we've got to benchmark the repeatability under laboratory conditions, for example, by doing a 24-hour batch. And these are for two purposes. We've got to evaluate the mean measured mass accuracy of this multiple analysis as an indicator of the systematic error, whether you're observing whether your instrument is under the influence of temperature fluctuation or any other sources of bias. And also we could use the standard deviation as a metric for system stability, i.e. the non-systematic error, if we use. And you could use this standard deviation as a basis to predict the expected range of mass measurement accuracy. So if the standard deviation was 0.2 ppm, you could expect that 99% of the data to fall within 3 times of the standard deviation, which is 0.6 ppm. And this sits around the mean measured mass accuracy. So if the mean was, for example, 0.6 ppm and standard deviation was 0.2, it's sensible to put the mass accuracy window as plus or minus 1.2 ppm, because you would expect by chance some of the data appearing at 0.6 ppm bias plus 0.6 ppm non-systematic random error. So this is how you should consider the mass accuracy window, and setting appropriate mass accuracy window is very important for effective compound identification for generating XIC of high signal-to-noise ratio. So this is my final slide, effortless performance LCMS-9030. Sorry, promotion again. So mass accuracy, sensitivity, speed are the attributes which we've particularly focused on in building this instrument, and we've implemented several technologies to achieve these, but due to limitation in time, I've only focused on mass accuracy. But mass accuracy is really the balance between resolution and sensitivity, and if we have time or opportunity for another webinar, I would discuss more on the technology for achieving high sensitivity and high resolution. So, because there are a lot to it, and thank you for listening to this presentation, and I hope I'll be able to present in front of you again. So the time is now open for a live Q&A session, and I hope you've come up with several questions for me to answer. And thank you very much again for listening, and thank you LabCorp for hosting this seminar.
Thank you, Dr. Toyama, for your presentation. A quick reminder for our audience on how to submit questions. Simply type them into the drop-down box located on the far left of your presentation window labeled Ask a Question, and click on the Send button. Dr. Toyama will answer as many questions as time permits. The first question is, what is the benefit of using ppm as a unit of error as opposed to m over z, for example, 400 plus or minus 0.5 m over z, instead of 400 m over z with 0.1 ppm error?
Okay, thank you for this question. So the benefit of using ppm as a unit of error is, well, there are two reasons for it. One is because by dealing with ppm, the number becomes larger. So typically we are dealing with mass measurement error, the absolute mass measurement error of about 0.0001 or 0.00005 or something in that region. So converting that number into ppm simply decreases the number of decimal places. And the difference between that and the second reason is because the same absolute mass error, mass measurement accuracy, doesn't exactly translate into the same significance depending on the M over G region of interest. For example, if you are to identify a compound of M over G 100, the error in that case, the error of 0.1 M over G is far more significant than the same amount of error for M over G of 1000. But it's more or less similar for when you convert it into ppm. So this is why ppm is typically used for mass measurement error.
Thank you. Next question is, which technology is used for heating?
So which technology is used for heating? I think this refers to the temperature control technologies used for the flight tube. So flight tube is like a thermos flask. The thermos flask is something such that the flight tube is contained within the vacuum, and the problem with that is that there is no physical contact point directly connected to the flight tube, and because the flight tube is applied with a high voltage, and having physical contact does reduces that insulation. So for that reason, you need to heat up. You need to control the temperature of the flight tube through radiation. So we heat up the housing of the flight tube and expect that radiation emitted from the housing transfers almost directly to the flight tube contained within the housing. So this is why radiation is an important heating method for the flight tube. And the nickel plating technology that I mentioned in the slide is something directly related to that. So actually in Shimazu Corporation, we have a different division, mechanical industrial machinery division. And one of the technology that has derived from there is this nickel plating technology. And this is used in the cooling of the turbomolecular pump. So this same technology is used in this flight tube to maximize the radiation efficiency.
Thank you.
So that's the end of my answer.
Thank you for that. Next one is, how many times is it necessary to calibrate or tune the instrument before starting analysis and at the end of the samples?
So from our experience, tuning, we don't need to perform frequently at all. The instrument is far more stable than we actually anticipated when we're developing this instrument. And in terms of calibration, we recommend a daily calibration, but daily calibration is far more sufficient than actually required. So it is certainly good enough to calibrate once every day. The first thing to do every day is to calibrate, and that's good for that whole day, and possibly for another day or two as well. But for keeping the routine, we recommend calibration every morning, but that's far more sufficient than actually required.
Great, thank you. What size is the quadrupole? 4K, 6K, or 8K? I hope I said that correctly.
Well, size of the quadrupole, right. So I suspect that's referring to the MFD, the mass range of the quadrupole itself. So by specification, we say that it's 2K. It's MFD 2000. We could do MS isolation, but for mass measurement purpose, MS1 measurement, the quadrupole can be set to allow passage of unlimited MOVD. So in total, as an instrument, the MOVD range, we can measure up to 40,000 MOVD.
Thank you. Next one is, what about isotope measurement accuracy?
Right. So I suppose that's referring to isotope measurement accuracy. I suppose that's referring to the reproducibility of isotope abundance ratio, which is a critical factor for elemental composition identification. So in that respect, our Q-TOF, particularly using the ADC detector, our Q-TOF is highly quantitative, and the isotopic abundance fidelity we are very confident with. So that hopefully answers your question.
That's great, thank you. Next one is, what are the precautions one has to take during analysis and after analysis?
The precautions to undertake during analysis and after analysis. So we've engineered this instrument to minimize things like that. So in terms of precautions, we even though we are fairly confident with how we control the temperature of the instrument, it is always recommended that the instrument is placed under a stable environment, stable laboratory temperature, and particularly to avoid direct contact with the aircon fan, so to say. That's something to care about during installation. And so during analysis and after analysis, there is not much to care, because if you are doing an on-the-fly calibration correction, then there's a lot to care about. But if you are doing external calibration, we don't need to recalibrate or to check if the calibration has been conducted correctly on the fly. So this is the easiest. This is the benefit of not using internal calibration. So we've tried to make things really easy.
Thank you. Next one is, what are benefits of using an analog digital converter over a time-to-digital converter?
Right. So having mentioned the ADC and the difference between ADC and time-to-digital converter, TDC, is that the benefit is that ADC tends to be more quantitative, because in principle it can integrate multiple ions within the same time bin. Well, that is for example, 0.5 nanoseconds. Within that time frame, ADC can accept multiple ion arrival and record them, whereas TDC tends to get saturated very easily. So ADC detector system should give highly quantitative signal intensity.
Thank you. Is there a library for identification?
So library for identification. Right. So spectral library, MS spectral library for identification. Yes. So the Shimada has been renowned for the triple quad in the triple quad mass spectrometers, and for the triple quad we have an MS spectral library database, particularly in the forensic field. And this spectral library developed for triple quad, the same spectral library can be used for this Q-TOF as well. And this is because we are using the same instrumental architecture up to the collision cell. So if we set the right conditions, if we set identical conditions for acquisition, then this library, MS spectral library, reproduces well to be used directly.
Thank you. Next one is, was the 60-hour stability data measured from standards in solvent or matrix?
Yes, 60-hour stability data. Okay. Well, this 60-hour data has been measured in neat standard solution, and there's a good reason for this. And this is a model experiment, and the intention of the purpose of this experiment is to evaluate the extent, the impact of system robustness on the data. So we've tried to eliminate the sources of systematic error. We've put the instrument under stable environment, and the instrument itself is temperature stable, and we're using ADT, and those are the concentration modified, concentration adjusted as well, not cause saturation. And those sorts of errors have been eliminated, so that what's left is the non-systematic errors typically caused by electronic irrobustness. So through doing that, we've shown that if we got rid of the obvious sources of error, the instrument is super stable to give a standard deviation in total of 0.2 ppm. So that's what we've shown, and the instrument is acting as intended, because we did observe no systematic bias throughout the 60-hour period.
Well, thank you. Looks like we have time for one more question. For what kind of application would mass resolution of 30,000 fall short for proper analysis?
Oh, that's a tough question, because 30,000 resolution typically sounds a little smaller than a competitor instrument. But however, we are fairly confident that 30,000 mass resolution does good enough job, provided that the mass measurement accuracy is good, and it indeed is good. So where it falls short is for applications like resolving the second and third isotopes of isotopic distribution, and that is needed when identifying the elemental composition by not using the isotopic abundance ratio. So rather than using abundance ratio, we could alternatively resolve the second isotope such that we could resolve the second isotope derived from carbon-13, or if it's derived from nitrogen-15. So this kind of thing can be done with ion cyclotron type mass spectrometers with hundreds of thousands of mass resolution. But that's something beyond the scope of Q-TOF instrumentation anyway.
Well, I would like to once again thank Dr. Toyama for his presentation. Do you have any final comments?
Oh, final comment. It's just how thankful I am to the audience for this great turn-up and series of questions that excited me. So thank you very much for attending this webinar, and I am very pleased to be able to present in front of you again.
Thank you. I too would like to thank the audience for joining us today and for their interesting questions. Until next time, goodbye.